You introduce yourself and proceed.
Sounds good. Good afternoon, everyone. I think it's afternoon for everyone now. Can you see my screen?
Yes, we can now.
Okay, good. Yeah, good afternoon. Thank you, Bob. Thank you, Scott. My presentation here today is use of, it's a big long name, long title here, use of field testing and CFD analysis to improve poor ammonia distribution and SCR performance. So I'm going to have a little outline here, just kind of cover some basic, very basic SCR operation parameters and typical stack limits, and then talk about the types of NOx measurements and tuning that we do, and are pretty unique in how we go about this. And then 2 case studies, which kind of use those same NOx measurements and 2 different problems on 2 different combined cycle units, but kind of cool how the measurements turned into a CFD model and turned into a solution. Okay, SCR basics. So SCR is the process of removing NOx, which is NO and NO2 out of the flue gas stream by injecting ammonia. The ammonia and the flue gas pass over the reactor, which is basically the catalyst, and you can see those 2 reactions that take place. Those are the 2 primary reactions. So ammonia is reacting with the NOx, the NO or NO2, in the presence of oxygen, and then we form nitrogen and water. Real simple process, been around for a long time. However, that ammonia, how that ammonia is introduced can be the subject of some performance issues. Now, in terms of typical ranges in performance requirements, I mean, it varies all over the place from state by state, utility by utility. Worldwide, there's just, an amazing range of parameters. But typical for CO can range anywhere from 2 to 10 parts per million NOx, 2 to 5. The newer units, of course, are going to be on the lower side. Ammonia slip, and we'll talk about a case study here where the ammonia slip is down at 2, which is becoming more common. VOCs, and then you can see the pressure drop requirements. So in a new system, these are usually the parameters that are given to an SCR supplier, whether it's a catalyst or the system supplier. And then the ammonia and NOx distribution is kind of a topic of discussion that we'll have here. And then catalyst life, you can see that's all over the place in terms of requirements. The AIG in the catalyst, or basically the SCR system, is located in the HRSG, where the temperature can range from 550 to 750. Of course, it can be on the higher side of that and the lower side to some extent, but these are the typical ranges of SCR application. The ammonia injection grid is used to distribute the ammonia air mixture, and that's coming in from a vaporizer system, an external skid mounted vaporizer system. And the objective is to distribute that ammonia air mixture into the flue gas as evenly as possible. It's typically located downstream of the CO catalyst if there is a CO catalyst present. And the AIG should be designed so that you can tune it. We're going to talk about tuning. And our theory is you should not have to tune an AIG in a combined cycle unit if it's properly designed and modeled, but you want to have that flexibility just in case. So why do we need good ammonia distribution? Well, this graph here kind of shows the general idea. You can see, so for the different levels of ammonia and NOx distribution, you can kind of see we start at a very even, so a perfect, I'll back up a little bit, percent RMS is root mean squared. So that's basically the standard deviation of the data set divided by the mean. So if you remember from statistics, if the standard deviation is low or 0, then that means every point every data point's the same. Well, in reality, we're never going to see that, but we can see some very even distributions in the field. And you can see there that if the distribution is really uniform, say it's 2%, for a 90% DNOx unit, your ammonia slip is going to be really low. It's going to be less than 1 parts per million. For the same catalyst, if the distribution is, and this is all relative, but for that same catalyst, if the distribution's kind of lousy and it's 12%, then you can see that your ammonia slip is going to be up more like 5 ppm. So this is just kind of gives you a relative understanding that the catalyst could be perfectly fine, but if the distribution coming into it is lousy, then you're going to have ammonia slip issues. So ammonia slip, so what? Well, it is kind of important because if you're overfeeding ammonia, you can drive your NOx down to basically 0. And you know, that's, you know, that could be something that somebody tries to do to maybe get under a permit limit, but it's never a good idea, because if your ammonia slip as a result of driving that NOx down is high, you're going to have 3 basic problems. You're going to have ammonia emissions exceedances if you do have a permit limit on ammonia, which most utilities do. You're wasting ammonia, and then our first case study is going to talk about HRSG fouling. So aside from you know, if your NOx is right within limits, say your permit limit is 2.5 and you're running at 2.2 and everything's great in the world, if your ammonia is high, you have other issues. So again, if you have a permit on ammonia, you could be meeting your NOx perfectly fine, but ammonia is an issue, and we see this countless times. So the causes of those ammonia or high ammonia slips or high ammonia slip levels are usually caused by 3 factors. It's poor distribution, which we'll talk about; bypass, where ammonia is sneaking around the catalyst in some areas, whether it's the walls or the roof or between the modules; or deactivated SCR catalyst. And that's kind of in the order of priority or experience. So deactivated SCR catalyst in a combined cycle unit, yes, it does happen, but it takes a long time. The deactivation rate on catalysts when burning natural gas is pretty low. So tuning, you know, once you establish what the ammonia and NOx distribution is, you can tune it. And so there's a couple of methods or standard methods for measuring NOx distribution. And this one shows kind of a stationary grid that would sit behind the catalyst bed. So here you can see the it's kind of hard to see, but they're just, you know, 1/4 to 1/2 inch diameter stainless steel tubes that would be arranged on the back side of the catalyst. And then these are at, you know, various points and elevations and depths. And then you draw, and then, you know, you bring in as a trailer, and you kind of draw samples, and then you kind of get a somewhat real-time look at the distribution. The problem, and I'll talk about the problem with those grids, if they're there, that's fine. If they're not, they're a headache to add. And you know, so on some new units, they're specified in there as being required, but you know, most existing units out there don't have them. So what we've been utilizing for several years now is a method where it's real simple. You're basically dropping a weighted test probe down through some sort of ports on the roof of the HRSG. So here you can see on the left, basically they're sky climber ports, which are, you know, almost always installed around the catalyst because of you know, access to get in there with a sky climber and clean the catalyst or initially load it or replace it, etc. So you can see there on the left, one of those ports. It's really exciting, but you can see the port there on the left. And then the guy there on the right is actually using one of those ports, which we'll talk about for this test method. The advantages of using this, it eliminates the need to add a permanent test grid. So again, if it's a brand new unit and the grid is in there, it's a very insignificant cost compared to the entire cost of the whole HRSG. But to add it in later, is no easy task. It requires outage time, materials, obviously, and then scaffolding on the inside and the outside of the unit to install. The other advantage is it's quick. This only takes 3 to 4 hours to do a full traverse, which we'll talk about. And then we can use FTIR, which is a standard EPA method 320 for measuring ammonia at any and all points. So we can measure that at the inlet and the outlet. And this is ideal for combined cycle units where the temperature is right where you need it to be. So we're not worried about any sort of reactions going on in our tubing. And here you can see and we'll talk about this in another our case study here. This is the grid of points you can get. Of course, you can get more points if you have more ports across the unit. You get more depths if you want to get more elevations, you get more resolution. That's perfectly fine. This one was a 5x10, so you got 50 data points on a 200 megawatt system, which was ideal for kind of addressing what issues existed. So our first case study that we're going to look at here, which kind of takes into account the test methods that I just mentioned, and then going steps further in resolving the issues. So this is a combined cycle plant, a 2-on-1 Siemens 501F gas turbine in the Southwest US. Reason we were called in was to address what the customer believed was ammonia distribution issues, which he was right. But the problem that they were seeing was high pressure drop in their HPIP economizer tubes, which they called module number 5. And you can see the design pressure drop for that section was 2 inches of water column, and they were typically running up above 7 inches when they'd have to go in there and clean, which was basically every spring. They'd have to get in there and ice blast the stuff away. And there's the stuff. I took this photo kind of crawling in under that section. You can see the heavy buildup of ammonia bisulfate in some of the tubes, not all, but it was pretty drastic. And the only way to get in there was to do ice blasting at the time when they were experiencing these issues. So again, you saw this picture before. We went in there, did this traverse from the top of the SCR. I think they had 5 ports across. So and it was about 70 feet tall. So we were able to get a good resolution of points across. We tried our hardest to tune it, and we couldn't. I mean, we just made very, insignificant improvements. But we saw the real patterns, and there were just extremely high ammonia concentrations on the outlet of the catalyst, well over 30 parts per million, and some of the sections that we just couldn't tune away. So, we basically told the customer there's something else going on here that we just can't fix with balancing dampers. So based on our recommendations, customer contracted with us to do a CFD study to really understand where the problems were developing and how to fix them. So it wasn't just telling the customer what the problem was, is coming up with a solution. So in essence, the problem with the system was there was a very large baffle at the bottom of the CO catalyst, and the flow in this photo here on the right is from right to left. So the guy standing there, the flow is going from his right shoulder to his left shoulder. And you can see there was about a 5-foot dead zone at the bottom of the unit that was basically structure in there behind one of the headers. And the ammonia injection grid was located about 4 feet downstream. They actually did take out one of the lower lances in an attempt to address this problem. And then on the sides of the unit, which is kind of hard to catch in a photo here, but there was also an expansion outward from the ammonia injection, from the CO catalyst at the ammonia injection grid. So the gas was just basically filling in the sides, the bottom where you see that big dead zone. And this is essentially what we're able to show with the modeling. So you can see the left view is a plan view, and you can see the red is the areas of high ammonia concentration. So the ammonia was kind of building up on the sidewalls where it was expanding outward. And then it was also concentrating on the bottom too. You can kind of see how it kind of bubbles along the bottom. And we were really picking those up when we were measuring in the field. And the sidewalls. So, that heavy ammonium bisulfate buildup on the tubes was really concentrated in these high ammonia slip areas. And again, there was nothing we could do with tuning to take it away, because the tuning was, I mean, the AIG did come in from both sides of the HRSG, which was good, but there was no way to, unless you start getting there and blocking holes, and the AIG, which was, we tried it with the CFD and was considered ineffective. So there you can see that the distribution along the sides. Also, if you notice, that rippling effect of the ammonia, which was actually very apparent because the ammonia, when it was coming out of the ammonia injection grid, just wasn't being blended with the flue gas. So you can kind of see these highs and lows, and this was right at the catalyst phase. And this is something that it's really hard to pick up when you're testing. We picked up the big, hotspot areas, but we couldn't pick up this stuff here. But we did notice that our readings were fluctuating quite a bit from point to point, which was a kind of a head scratcher, but this made it make more sense. So just not getting in all of the iterations, but basically what we ended up doing was we had to take the AIG that was in there out. They were having some other issues with pluggage, and there was just no reason to save it. So what we essentially did was just move the ammonia injection grid upstream by 3 feet, closer to the CO catalyst. So there wasn't any ability for the flue gas to kind of sneak around the AIG, kind of fill in the sides, and then same with the bottom. And then we also put some baffles around the CO catalyst frame to make sure the gas was kind of channeled into the ammonia injection grid. We kind of boosted some of the mixing at the SCR catalyst by putting some just simple plates on the ammonia injection grid. You can see there those mixing baffles or plates, whatever you want to call them. And then there you can see kind of the finished product. So from the CFD information, you can see the ammonia distribution that we started out with was 70% RMS, which is pretty terrible. So it was easy to improve it, but the question is, how far do we go? And just some of the change in the ammonia injection grid got the distribution to around 10%. And then from there, we were able to just sneak it down to, close to 6%, which was great. Met the catalyst supplier's requirements, and you can see the pressure drop. The existing pressure drop caused 0 because it's just, they're just 2-inch pipes and, a very large duct. And all we did was really the mixing baffles just added a little bit of back pressure, but you can see there it's pretty small in comparison to the improvements. So then from that point, it was, okay, here's the solution and we need to fix it. So we were given the contract to design the new AIG, and then we had to do all these steps in basically 4 weeks, which was pretty hectic, but we're able to do this, and we needed to complete both units in a 2-week outage, so that required round-the-clock construction. And there you can see, the work that was done. This is a 3D model of what was actually modeled with CFD. Created drawings, fabricated the pipes, the mixing plates, center of support, and there you can see some of the end work there. You can see the scaffolding in there to cut the old pipes away and install the new, and that's essentially what the new system looked like. And here's the most important part. What did we achieve? Well, we got the ammonia consumption down, which was a result of reducing the ammonia slip. We cut the ammonia slip in half, and you'll probably notice that the ammonia slip, for starters, really wasn't bad on average, but we were able to basically cut it in half. The real issue was those high ammonia slip pockets, and we were able to get rid of those. And according to the customer, they were, the ammonia injection grid retrofit went very well. they had improved NOx control, and that ammonia salt formation dropped off significantly. So they really, from having to clean the tubes once a year, they basically have stretched that out to on an as-needed basis. They're not even doing it on a regular basis because the amount of ABS buildup on the tubes has dropped off dramatically. So that's one way to use testing and CFD to solve a problem, which was kind of unique in having this this ammonium bisulfate buildup. The next case study didn't have any ammonium bisulfate buildup, so they had some other issues here. So this is a plant in the Northeast. It's a single 101 501D gas turbine, and was installed in '94. Smaller plant, output of 200 megawatts. I had a HRSG with SCR that was also installed in '94. And in 2019, they installed dual function catalyst, and I'll explain why they did that. So due to some other unit upgrades, basically they added duct burners. They were set with some new emissions requirements by the state to some pretty aggressive levels. So you can see the old requirements. If you look at NOx and ammonia, so they were at 9 ppm NOx and 10 ppm ammonia slip. Well, that's pretty much a slam dunk for SCR. The new requirements were 2, 2, and 2, which were very aggressive, even for a new unit. So basically, we've got this old HRSG with an old SCR that's being asked to do some pretty amazing reductions. So the customer, rightfully so, added in new dual function catalyst to get to those levels. So it was designed for, for 2, 2, and 2. Unfortunately, when they started up, they were not, they were well ahead of schedule in terms of adding the catalyst, but they were way off on being able to meet those requirements. So plenty of testing and, evaluation of the catalyst was done. And the conclusion was the catalyst was perfectly fine. It's the problems were system related. So there you see those test ports again. So what we did, first thing we did was do a traverse to see what the distribution really looked like at the SCR. And that's the 5x10 array that I showed before. So we got 50 data points. And what we found here was with those 50 data points, I'll emphasize it's only 50 points, the distribution was about 19%, not very good. Had a lot of unstable readings. The ammonia slip in some areas was quite high on the outlet and very low on others. So based on that, kind of the same thing as we saw with the other project, we couldn't tune it. I mean, they only had 5 control zones anyway, so it was virtually impossible to make any sort of adjustments to make these problems go away. So we did CFD modeling, and we went all the way back to the turbine. We got the exhaust profile. We modeled all the tubes, the duct burners. We didn't really model the firing case because it really wasn't so much an issue, but we modeled the geometry of what the duct burners would do to the gas flow distribution. And of course, the existing AIG and catalyst. We did a very detailed model of the AIG, and you can see the AIG was basically in 5 sections. Those are the 5 control zones. So we modeled each one individually, and we saw a pretty pronounced imbalance of ammonia distribution within each AIG, which was a problem because that just carried itself down to the SCR, to the catalyst, I should say. What we also noticed, and we built this into the model, was these blockages. Now, they might seem insignificant, but they were pretty significant in terms of creating some poor ammonia distribution. So they had C channels in here, and they had horizontal tube steel, which is very strange, but it's going back 20 plus years. So I guess it seemed like at the time they were just wanting to make sure structurally this thing was going to hold together, which it certainly did, but created some issues with distribution. And here you can see, I just kind of put the drawing on the left and the CFD results on the right, and you can see those stripes of high ammonia were just sitting behind the C channels and the horizontal tube steel, and it was just creating a mess in terms of distribution. And also that same sort of ripple effect that I mentioned before, same thing. There was just no or very limited local mixing. Plus the AIG was very close to the catalyst. It was only 5 feet away. So there was just a compound of, bad stuff going on that created some poor distribution. And so when we modeled this, we said, okay, let's look at this, the 50 points that we measured in the field, and we got a distribution of 18% RMS, which agreed pretty well with the field measurements of 19. But if you look at all the CFD points, it takes into account, hundreds of thousands of data points. The RMS was actually 26%, which is even worse. So what we did in the field was fine for identifying where the problems were, but the CFD really helped to pinpoint, just the distribution was worse because we weren't picking up all the highs and lows. So redesign the AIG. This was part of the CFD that rolled into engineering drawings. We put mixing baffles on to kind of boost the turbulence. And final results from the modeling show that we were able to get the distribution down to about 6%, which is phenomenal compared to where it was. And you can see the difference between all CFD points and the 50 data points is basically the same. So that's saying we're not missing anything. We're not our field measurements aren't going to be misleading in terms of how good or bad the distribution is. So then the turnkey retrofit installation took place, worked with SCI Dynamics to basically redesign the AIG, demo the old. We had to take out the SCR catalyst because there was some other bypass issues going on there, which I won't get into. There's a lot of work in this this little 2-week outage, and but the thrust of the job was to take out the old AIG and put in the new, and this all had to be done in a 2-week outage, working around the clock. There's a picture of the new AIG, and here's the most important part: is the results. And the CO was never really an issue before or after, because the CO coming out of the engine was pretty low to begin with, but it was a dual function catalyst, so it was working fine. The NOx, they were to get below 2 ppm. Well, prior to this retrofit, they were struggling to keep it at 2, and then the ammonia slip was 3 or higher. And now after the retrofit, they were comfortably able to stay under 1 ppm with the ammonia slip, and the NOx, they could control it to 1.7 pretty easily. And the plant took this upon themselves to make some operational changes to kind of increase the NOx coming into it. So they were playing all sorts of, economic, going through a lot of economics to figure out what was the best way to do this. But this gave them tremendous amount of flexibility, and they were pretty happy with the results. So what they did require us to do is to go and say, we needed to prove that what we modeled was correct. And sure enough, we went in there and we did our same measurements that we did before, coming in from the roof, and the 19% dropped to 6%, and which was great. And there you can see we kind of laid the field test results on the left and compared those to the CFD results. And although the distributions aren't identical, the gross, I guess, overall values in terms of distribution were really a great agreement, both sitting around 6%, which was great, and it was exactly what we were trying to achieve. So that's the conclusion of my presentation. And Bob or Scott, I'd be happy to entertain any questions you guys might have.
Yeah, Scott. Yeah, Bill, thanks very much. We got a few questions here, I think. Scott, there's some here without a name on it, just sent by yourself. Is that correct?
That first question is from Jason McKenzie.
Don't see that. Okay. Are you going to put in, Mike?
Okay, Jason, you can unmute yourself if you want, or we can just ask the question.
Yeah, can you hear me okay?
Yeah,
Yep.
you're fine.
Yeah. I was just asking, or I'd sent to Scott, how do you achieve isokinetic sampling with a non-fixed probe, and or is that not relevant in this testing situation?
Yeah, it's not really relevant in this testing. So, this is, we always try to clarify this is not a compliance test measurement. We're really trying to get a gauge on the relative distributions within the SCR in terms of gas flow. Remember, the gas flow in the SCR is pretty low velocity. So we do use a weighted probe to kind of get the probe down. And I mean, some of these units are close to 90 feet tall. We're going to be testing one next week it's about 95 feet tall. We're also measuring temperature. That's something else I meant to mention, that temperature is another valuable piece of information. But yeah, the idea behind these measurements is relative performance of NOx and O2. And if you're using a grid, which I mentioned before, it's another way to do this, and it's fine. I mean, you can use a grid to measure. You're in the same boat. Basically, you have a fixed probe, and you're pulling a sample at a fixed location. We're doing nothing different. But I mentioned before, the temperature is kind of important, because if you're going above, say, 800, 850 degrees, you could start to convert ammonia to NOx in your probe. So that's why this is ideal for a combined cycle. For a simple cycle, you got to take a little bit different approach. But anyway, hope that answered your question. It's more of a diagnostic measurement rather than a compliance measurement.
Thank you. Thank you.
Good.
Sure.
So, Scott, there's a question from Ian Mylanbush.
Oh, hey, Ian.
Hey, Bill, I had a question about your first case study, looking at that ABS formation downstream.
Mhm.
Can you give a little bit of information about the fuel and maybe backup fuel?
Yeah, it was 100% natural gas, just pipeline gas. This is in Nevada. And so, we're talking very small amounts of SO3. That really wasn't the issue. It was the very high concentrations of ammonia that we saw around the perimeter. And this problem existed since 2002 when they started up. It was a yearly cleaning to address the ammonium bisulfate issues, which, yeah, I mean, I was surprised. The first question I asked him, are you burning oil? Was this a high sulfur oil? Then you went to low sulfur, and it's in the middle of the desert, so it was 100% pipeline gas.
Wow, pretty significant.
Yeah, sure was.
Thank you.
Yeah, sure.
Thanks, Bill. We have one from Tam Chelvan. He's got his hand raised.
Okay, the question and comment. The comment is for the case study 1, where you state that the ammonia bisulfate in the back end tubes were cleaned every year, but the pressure drop, back pressure was going up even after they clean. I think it's because the CO2 ice blasting is effectively cleaning only the front few rows, like 1 or 2 or 3 maximum rows, and the
Mhm.
deeper bundles never get cleaned. So as the year goes by, it gets accumulation of more and more debris, and that's why it's increasing the pressure drop. That's the comment. And we have seen multiple units of that nature. So they spread the tube, and then they reach the inner bundles, and then they clean, and then the pressure drop goes down. Okay, so that's the comment. The question is on the case study number 2. You mentioned that you removed all the big section of structural members to minimize the maldistribution. And so when you remove those big structural member, how do you replaced for the structural integrity of the whole system there with your new design? And then another question is, who is the provider of those dual function catalysts? I know there are 2 companies. One is Cormetech, another is Halder Topsoe. Whose catalyst was that? Those are my questions.
To answer that question, one of those 2. How about that?
Okay. Okay.
So I probably shouldn't say, but both companies that we know about have large database, large experience lists, and they've had good success. So kind of backtracking to your question about the ammonia injection grid. So the existing ammonia injection grid was completely removed, including its structure. It was all carbon steel, so that was all taken out. And then we started with a blank slate in terms of how to install a new ammonia injection grid. And a new ammonia injection grid on a new HRSG is not going to have that heavy amount of structure. So the AIG was designed to basically be self-supporting. We did install a center support column or tower, if you will, to support the ends of the AIG lances because they were coming in from both sides, and to allow for thermal expansion both horizontally and a little bit vertically. So it didn't need all that structure to begin with. I think the original OEM probably just didn't have a lot of practical experience, so they ended up putting in just a huge amount of steel that would never be installed in a unit like that today. Now, and then backtracking to your first comment, which the customer knew where the problem was because ammonia bisulfate only is going to deposit with the right temperature conditions, that 400 to 450 degrees. So they knew that it was deep into the bed of that bundle number 5. And so when they did their cleaning, they did exactly what he said. They did all the tube spreading, and it was expensive. And probably the ice blasting itself was the easy part. I think it was the scaffolding, the tube spreading, and the amount of time just spent trying to get in there and clean those out. And it was just a major headache. So, but yeah, I mean, after the outage, pressure drop was down. It never got down to the design basis, but it got low enough where they were comfortable. But then it would just creep back up, like you were saying. So.
Thank you.
But yeah, good comment, so Tim.
Yeah.
Yeah, thank you. Thank you, Bill. There's one question from Dan Morgan. We can, and there's Mike.
Thanks, Barry. Bill, you had mentioned in case study number 1 that that the customer was having trouble with AIG plugging. And those are pretty impressive RMS numbers down to 6%. If the pluggage continues, that RMS number, of course, naturally will go up and deteriorate some of the gains that were made. What was done to address the root cause of that pluggage, and does the customer need to do any periodic maintenance, or is there a trigger that they watch? Maybe it's simply ammonia slip or something else that initiates that periodic maintenance?
Yeah, no, that's a great question. So the ammonia system, and this is kind of typical, the ammonia system, all the piping was carbon steel, including the ammonia injection grid. So during shutdown, I mean, these are cycling units. They're in the middle of the desert. There's all sorts of solar out there. So, they're up and down every day. There was just a lot of rust scale that was coming in and blocking the holes in the AIG. Well, the holes in the AIG were actually small, and they were actually arranged where they were kind of on the 6 o'clock position of the pipe. So any sort of buildup was just kind of sitting on top of the hole. So they would have to try to get in there and just bang them out and vacuum them out. So we told them we can't fix that, but we did make the new AIG out of stainless steel. So we kind of got rid of whatever sort of rust or scale would come out of the AIG itself, which isn't a lot, but it's something. And then they also had us add in cleaning ports in the AIG, and it was actually in one of the slides I could show you, where they wanted cleaning ports in each lance to address this problem. So we just put in a threaded pipe cap and a nipple so they can go in there during an outage if they needed to, and just kind of bang on the pipe and vacuum out each section of lances. So, and then we rearranged the holes in the lance such that they were larger diameter, plus they weren't at the 6 o'clock position. They were like at 2 and 5. I don't know if I get my clock right, but they weren't on the bottom of the pipe. So at least if there is any buildup inside the pipe, it wasn't just sitting on top of a hole. And then their means of making sure that this was not a problem is their inspections. So they still are doing, spring and fall outage inspections on the AIG just to make sure they're not seeing any sort of unusual buildups in the AIG. And from the last I heard, it's actually working out pretty well.
Thank you, Tan. Thank you, Bill. Tam has his hand raised again. Mr. Silva.
No, that's by mistake. So I was deactivating my hand raise, but it activated. Okay, thank you.
Yeah, thank you.
Yeah.
Scott, I don't see any other questions.
Gary, I've got a couple if I might.
Oh,
This
go
is
ahead.
Bob. So Bill, you mentioned in both case studies that you added gas distribution plates on the new AIGs. Is there any significant pressure drop associated with that revision to the design?
Yeah, that's kind of like the limiting factor is how big do you go with the distribution plates. So if in the one project, the one in the desert, the first one, the original AIG, call the pressure drop across it, and this is from CFD. We didn't measure the DP in the field. It's a little cumbersome to do that, but in the model we're very comfortable with those results. The pressure drop across the existing AIG was basically 0. I mean, you couldn't even measure it because it's just like 2-inch pipes sitting in very low gas velocity, so it was very low. With the mixing plates, it added about 0.2 of an inch, so it's pretty relatively minor. But that's kind of like the that's kind of the parameter that you're looking at. The bigger the plate, the better the mixing, but the more pressure drop. So you kind of have to balance it out to figure out what's the limiting factor.
Then at the beginning of your presentation, you mentioned a permanent monitoring grid. Is there a economic benefit to frequent monitoring of slip, or is continuous monitoring of slip possible? And if so, is there an economy in keeping things tuned and seeing developing trouble early?
Yeah, doing this method for measuring your overall ammonia slip, and we've done this countless times where the stack ammonia slip measurement was reading something. We went in there and we measured 50 data points. We're in the stack, they're measuring 1 or 2, and we're seeing numbers that are either higher or lower. But we've got 50 data points, they've got 1 or 2, so we're going to rely on our numbers because we're using a very reliable instrument, the FTIR. But if the client does not have a permit limit on ammonia slip, then they're either going to measure it and be good guys and determine what it is, or they're going to use some sort of calculation method, which they can be terribly wrong, the calculation method, because you're looking at inlet NOx and ammonia flow, which, they have some variations to them. The ammonia flow can be off. So, even if the plant does not have a permit limit on ammonia, it would be great if they could measure it. And those instruments to measure ammonia slip in the stack are not terribly expensive, some of them. So that would be the best way. But, sometimes when you measure, if you're measuring ammonia slip and you don't have a permit limit, you're kind of opening the door to having to report it. So, we don't want to push for that too much. But this method here works great if you're trying to diagnose a problem. If it's like an annual, what is my ammonia slip, you're better off going to the stack to measure that.
Yeah, I was thinking more of their, for example, fouling of the downstream tubes in zones where you've got high slip. If there's an economic benefit to, say, if you're building a new boiler to put the permanent monitoring grid in.
Oh, okay.
Is that likely to pay for itself? Not so much from an emissions reporting standpoint, but from just being aware of what's going on that might cause other problems.
Yeah. Okay. I think I understand a little bit better. The permanent grids, in a new unit, there would be perhaps some benefit to installing those as opposed to doing this traverse method. The thing is, you still have to bring a trailer in. You still have to, knock out moisture. I mean, there's a lot of things that you just can't avoid by having that permanent grid. But I'm working with a client right now on a brand new HRSG, and they're wanting to have as many ports on the roof as possible to do this. So to answer your question, the grid is okay. Doing this method here is also going to give you more flexibility because you can increase the resolution of the points, whereas the grid, I mean, you're just going to add in a tremendous amount of tubing into the back of the unit that kind of gets in the way and gets banged up after a while. But yeah, it's just a good idea to be able to monitor this. And with the the ABS fouling issue, nobody ever knew that was going on until this was tested. So to have that information, I think would be pretty valuable.
Yeah, thanks.
Sure.
Well, I see no more questions. Yep. Anybody got another question for Bill? All right. Well, thank you, Bill. Very, very good. Very informative.
Yeah.
Thank you.
My pleasure. Thanks, guys.
We've got just a few minutes left. Has anyone got any questions about anything else HRSG related? Either put it in the chat or raise your hand.
There's a few. There was a few on the registration list, but I think that we covered those.
Okay. All right. Well, I don't see any more. Okay. If you think of something in the next